The concept of a warp drive has long been a fascinating idea, drawn straight from the realm of science fiction. First introduced as a theoretical framework by physicist Miguel Alcubierre in 1994, it is based on the idea of bending spacetime to achieve faster-than-light travel without violating the laws of relativity. Now, recent breakthroughs are bringing this once-distant concept closer to scientific reality. Innovative research is reshaping what was once thought impossible. New models have eliminated the need for exotic negative energy, while advanced simulations are shedding light on how warp bubbles might actually function. In this video, we'll explore the latest developments in warp drive research, explain the science behind its potential functionality, and uncover why these discoveries matter for the future of space exploration. The evolution of warp drive theory. The idea of a warp drive, allowing faster-than-light travel by distorting spacetime, was first proposed by Mexican physicist Miguel Alcubierre in 1994. His theoretical model suggested that contracting space in front of a spacecraft while expanding it behind could enable superluminal travel without violating Einstein's theory of relativity. However, this concept required exotic matter with negative energy densities, a substance not known to exist, making the idea seem unattainable. Fast forward to recent years, and warp drive research has undergone a paradigm shift. In 2021, physicist Eric Lentz proposed a groundbreaking model that challenged previous assumptions. His work suggested that superluminal travel might be possible without the need for negative energy. Instead, his model relied on known physics, utilizing structures called solitons, stable, localized wave packets that travel without dissipating energy. By configuring these solitons within the framework of general relativity, Lentz demonstrated a theoretical mechanism for generating a warp bubble using positive energy sources. This approach adheres to Einstein's equations while bypassing the need for hypothetical exotic matter, bringing warp drive technology closer to feasibility. Building on this momentum, researchers at the University of Alabama in Huntsville, UAH, made significant strides in 2024. Led by Dr. Jared Fuchs, the team published a study demonstrating, for the first time, that a subluminal, slower-than-light warp drive is possible within the bounds of known physics. Their model eliminates the necessity for exotic matter or negative energy, instead relying on conventional energy sources to create a warp bubble. While this subluminal approach does not achieve faster-than-light travel, it represents a monumental leap in our understanding of spacetime manipulation and propulsion technologies. It lays a tangible foundation for future research, potentially paving the way for practical applications in space exploration. Computational tools advancing warp drive research. As theoretical models evolve, the need for advanced computational tools to analyze and simulate warp drive scenarios becomes increasingly important. Enter Warp Factory, an open-source computational toolkit developed by the Advanced Propulsion Laboratory at Applied Physics. Unveiled in 2024, Warp Factory is designed to model the unique physics of warp drives, providing researchers with a platform to explore various warp drive geometries and their physical properties. By numerically solving Einstein's field equations, this toolkit enables scientists to examine the feasibility of different warp drive configurations and estimate their energy requirements. The ability to visualize these complex spacetime structures in both 2D and 3D provides invaluable insights, helping researchers better understand how warp bubbles could be generated and sustained. This tool marks a significant step forward, transforming theoretical equations into tangible models that can be studied and refined. In parallel with these modeling advancements, researchers have also explored the potential observational signatures of warp drives. A study published in the Open Journal of Astrophysics in 2024 took a novel approach by simulating the gravitational waves that a failing warp drive might produce. With each new breakthrough, warp drive research is steadily moving from the realm of science fiction into the realm of scientific possibility. While there is still a long road ahead, the advancements in theory, modeling, and simulations are bringing us closer to understanding whether warp travel could one day become a reality. Gravitational waves are ripples in the fabric of spacetime, typically generated by massive, accelerating bodies such as merging black holes or neutron stars. A recent study suggests that a malfunctioning warp drive could produce a distinct burst of gravitational waves, characterized by a short, high-frequency signal. While current detectors may not yet be sensitive enough to detect such signals, This research provides a framework for future observational strategies. Identifying these unique gravitational wave signatures could potentially confirm the existence of warp drive phenomena or help diagnose issues in experimental setups, bridging the gap between theoretical models and empirical evidence. Despite recent breakthroughs, significant challenges remain in developing functional warp drive technology. The most daunting obstacle is the immense energy requirement. Even with models that rely on positive energy, the amount needed to generate and sustain a warp bubble is astronomical. Early calculations suggest that moving a small spacecraft across the Milky Way would require energy equivalent to 10 kg, surpassing the total mass energy of the observable universe. While newer theories have reduced these requirements, finding a practical and efficient energy source remains a critical focus. Potential solutions could involve advanced nuclear reactions or harnessing zero-point energy fields. Another major challenge is the stability and control of the warp bubble. A spacecraft must safely enter, navigate, and exit the bubble without harmful effects. Theoretical models must account for potential instabilities caused by quantum fluctuations or interactions with interstellar matter. Additionally, developing precision control systems is crucial for accurate navigation and safe deceleration. This requires a deeper understanding of spacetime dynamics and the creation of technologies capable of manipulating them effectively. One particularly promising area of research is antimatter propulsion. With its incredibly high energy density, antimatter releases vast amounts of energy when it collides with regular matter, making it an ideal candidate for highly efficient propulsion systems. However, producing, storing, and safely utilizing antimatter presents enormous scientific and engineering challenges. These research efforts highlight humanity's relentless drive to push the boundaries of possibility. While an operational warp drive remains out of reach, every breakthrough in propulsion technology, quantum physics, and spacetime manipulation brings us closer to making this futuristic concept a reality. Looking ahead, the future of warp drive research hinges on several crucial developments. First, scientists must drastically reduce energy requirements, possibly by discovering new states of matter or energy. Second, more advanced computational models are needed to simulate warp bubbles and their interactions with cosmic environments. Finally, global collaboration will be essential, combining resources and expertise from around the world to tackle this monumental challenge. Why does this matter? Achieving faster-than-light travel could revolutionize our understanding of physics, potentially bridging the gap between quantum mechanics and general relativity. Such breakthroughs could also drive technological innovations in energy, material science, and computation, benefiting life on Earth in ways we cannot yet imagine. Most importantly, a functioning warp drive would redefine humanity's place in the cosmos. It would mark the dawn of an era where interstellar exploration becomes reality, allowing us to venture beyond our solar system, discover new worlds, and confront the mysteries of the universe head-on. Let me know if you want any further refinements. Rocket.